So I want to start by picking up from where we left in the last lecture. And that is, it may be helpful to refocus a little bit on this term here, the second term, when we break up the maximization problem that we had into current reward and a max over feasible plans for the future starting in period t equals 1, right? So let's do that a little bit more generally and ask ourselves, what is the discounted present value? What is the maximum discounted present value to the decision maker of a maximization problem that looks exactly like this, but the decision maker has arrived at some period capital T and inherited a state X subscript capital T, right? So let's put that down. So let's say the decision maker wants to maximize. So this is a different discussion, right? Wants to max the following, or let's say the decision maker is now in period capital T and wants to maximize this discounted present value. So f of x capital T plus 1 plus beta times f of x capital T plus 1 x capital T plus 2 plus beta squared times f of x capital T plus 2 x capital T plus 3 plus discounted present value of these returns, subject to the state that has been inherited. So subject to xt given and feasibility, right? So feasibility would be that xt plus, so let's choose a different index here, so plus s plus 1. This state must be chosen from the set of feasible states starting from the state x capital T plus s. And this must be done for all s starting with 0. So do you see that if I put s is equal to 0, I get x capital T here. So that is saying that gamma of x capital T is the set of feasible states available to the decision maker at time capital T, okay? And that is all the x capital T plus 0 plus 1. So all the x capital T plus 1 available at time capital T, okay? And then you let small s step through all these indices. Right? So suppose this is the problem. This is the problem in at time capital T, right? So what is the claim that we used above? So the claim was the max equals V star of x capital T, okay? Where the value function V star is defined by for all states x, V star of x is equal to max summation beta to the t f of xt plus 1, t going from 0 to infinity, yeah, subject to x naught is equal to x given, and xt plus 1 at any t plus 1 is chosen out of feasible xt's, right? Yeah. So that's the value function derived from the decision-making problem at time t equals 0, right? So we're saying, suppose the decision-making problem now is at time capital T, okay? So the decision maker has a discounted present value over rewards or returns from capital T to infinity, okay, and starts with x capital T, right? So the assertion is that the max here will be nothing but v star of x capital T. So in particular, this functional form for the value function is exactly what it was at time t equals 0. And we said that, look, this is bound to be because when the decision maker sits at time capital T and stares into the infinite horizon, the decision making problem is exactly the same, except that at time capital T, the initial capital stock, or at time capital T, the initial capital stock or the initial state is x capital T, right? So more formally, in order to see this, we rewrite first the discounted present value. So we rewrite this as so let's say maximize summation starting at capital T. So let's say our index now is small s. So small s starts at capital T, goes on through infinity. Beta raised to the s minus capital T, f of xs plus 1. Okay, so check that this is exactly what's happening here. Okay, so when small s is equal to capital T, we have x capital T plus 1. That's the term here. And beta small s minus capital T is then beta raised to the 0. Okay, so that's saying that there's no discounting when the decision maker is sitting at time capital T, right? And then we increment the s here to capital T plus 1 and so forth, right? So check that this is exactly that objective function, right? And now make the following change of variable. So now make the change of variable small t, let small t be equal to s minus capital T, okay? And this will also mean that small s is equal to t plus capital T, okay? And it will also mean that s is equal to capital T implies small t is equal to 0, right? So using this change of variable, this is max. So I want to replace the s and the s minus capital T with a small t, okay? So max small t is equal to 0. So remember, when s is equal to capital T, s minus capital T is 0. Okay, so small t is equal to 0. When s goes to infinity, so s goes to infinity, so does t. Right? Beta raised to the small t. F of x t plus capital T, x t plus 1 plus capital T. And you can write the feasibility constraints in, but now you see that, you know, this objective function with given x capital T and feasibility, is an infinite horizon problem. So is the infinite horizon problem starting at t equals 0 with initial state x capital T, right? So see that, you know, if t is equal to 0 here, the initial state is x capital T. So it's the max value is equal to v star of x capital T. So we had used this argument to substitute here and say that, look, the max value here is nothing but v star of x subscript 1. Okay, all right. So we have a short digression on series, which I will also discuss very briefly. And by way of motivation, you know, our objective function, so this should be a t equals 0. Our objective function in these infinite horizon problems is going to look like that. So more generally, you know, there is some term here at each t. Let me call this term, so let me change this to, you know, what we are looking at is something like summation of terms. There is one term every period. That's, let's say, a subscript t, right? So we're looking at something like this. Okay. Now, I'm going to make a change of notation which is completely inconsequential. The change of notation is partly to help you if you look at treatments of series in analysis books. You don't really have to, but if you do, then, you know, in those books, sequences will be typically indexed by n, right? Sequences will be written like this. And so we are going to change notation just for this section to looking at series as something like that. Okay. In another sort of, you could say, notational change will be that, you know, in most analysis texts, sequences are treated as sort of functions going from the natural numbers to something. Here, natural numbers to the real numbers. So since natural numbers, we're going to change the indexing and let it begin at 1 rather than 0, which is completely inconsequential in an infinite horizon setting, right? Okay. So now we want to ask what this infinite sum really means, or in new notation, what this infinite sum actually means, right? So it means the following. So I have to start with an underlying sequence of the ANs, okay? And I'm adding them all up. Yeah. But to define what adding them all up means, we will use that it means that this is the limit of a sequence of partial sums. So what are these partial sums? So I start with this sequence, or I look at this series and I say, look, my first partial sum is just A1. My second partial sum is the addition of A1 and A2. My third partial sum is the addition of A1, A2, and A3, and so forth. Okay, so if this has a limit, we'll say that we'll represent that limit as this infinite summation, A1 plus A2 plus A3, etc., etc. Okay. Now, if all of these are non-negative, so if all the ANs are greater than or equal to 0, we don't need to bother all that much. Okay. Not much of a problem. So why is that? It's because then the partial sums are an increasing sequence, right? So A1 plus A2 is greater than or equal to A1, A1 plus A2 plus A3 is greater than or equal to A1 plus A2, and so forth. So if these are bounded, then they converge to their supremum. If they are not bounded, the limit goes to infinity, and we can either say diverges or converges, whichever we like, to infinity, right? Okay, but other than that, there is no problem. So if we say that convergence includes convergence to infinity, right, and our sequence, our series has only non-negative terms, then it's always going to converge either to a real number or to infinity. Okay, that's not that much of a problem. A problem arises when we have some positive and some negative elements. So why does that bother us? If we are just maximizing utility, can't we just take utility to be non-negative through some uh, even if negative, through some increasing or some positive affine transformation? The point is, it's not that we will always be maximizing utility. We could, for example, firms could be maximizing profits could be positive and negative, and there could be lots of consumer problems also where the objective function is not necessarily positive in each period, right? So we need to consider problems that happen if some of the terms here are positive and others are negative. So the simplest example is that of the sequence of alternative ones and minus ones. Okay. And if we write that as a series, it looks like that. Okay. And that's called Grandy's series. And you can see that there's a problem in adding these up because it depends on how you're doing the addition, right? So suppose I add this to this, I get a 0, then I get a 1, 0, okay? There is a problem. We don't even, so for example, what does this mean and where does it go? If you say that it goes to that, well, maybe. Alternatively, if you use brackets like this, then this, these are zeros and this goes to 1. So to circumvent these kinds of problems where I can't just put brackets as I like if the sum is infinite, right? Remember that the associative property is done with in any set is done with 3 elements. Okay, so I can extend that to a finite number of elements, but I'm not sure what extending to infinite numbers of elements is right now, right? So a sensible way is to see, well, what happens to the partial sums. So if you look at the partial sums here, and give partial sums now a name. So let's give a name to the partial sums. So if I add up the ans from 1 to t, I call that a partial sum, st, right? So a1 plus a2 all the way through at, I'm going to call that st. Right? And then this series, or this infinite sum, is defined as the limit of st goes to infinity, right? So if I look at this series here, I can see that S1 is 1, S2 is 1 minus 1, that's 0, S3 is 1 minus 1 plus 1, that's 1, S4 is 1 minus 1 plus 1 minus 1, that's a 0, right? So the sequence of partial sums looks like 1, 0, 1, 0, and so forth. Right? It doesn't have a limit. Of course, it has lim sup and lim inf, but it doesn't have a limit, right? So that gives us this first definition, conditional convergence of a series. A series is conditionally convergent if the sequence of partial sums converges. So this Grandy series is not conditionally convergent. However, the series 1 plus half plus 1 by 2 squared plus 1 by 2 cubed, etc., we know, we can establish converges to 1 over 1 minus half, that's 2. Okay, so this series is conditionally convergent, right? So there is a stronger definition of convergence, and that has to do with the convergence of the series that we obtain from the original one by replacing the ANs with their absolute values. Okay, so replace is replaced by absolute values, and then this series is just, it just has all non-negative terms, and we can ask, does it converge in the traditional sense of does it converge to a real number? Yeah, that's the that's what we are using in this definition. So does summation absolute AN converge to a real number? Yeah. If not, then we saw that it diverges or converges to infinity. Here, in the way that this definition is stated, convergence is to a real number. So absolute convergence of a series summation AN is absolutely convergent if summation of the absolute values converges to a real number. Okay, so that is the sequence S tilde T of partial sums of the absolute values converges. Okay, so we saw that Grandy's sum is not conditionally convergence. The partial sums repeat 1 0 1 0 etc. If we look at the absolute values for Grandy's series, that was Grandy's series, right? So I replace all the terms with their absolute values and I will get this. Yeah, does not converge to a real number, right? It diverges or converges to infinity. All right. So here is one, very well-known example of an alternating harmonic series, which I encourage you to look at. It has the following property that Grandy's series does not. That if you look at this alternating positive-negative series, it actually converges in the sense that the sequence of partial sums converges. There are various ways to see this, but one way to see it is that I can get this series by doing a Taylor expansion of natural log 1 plus x, and then replacing x with 1. So that will show that this is the Taylor expansion of natural log 1 plus 1, which is log 2. Yeah. There are other ways of showing that the series converges. One way is you take odd and even subsequences and show that they converge to the same number, etc. Yeah. The point is there is conditional convergence to log 2. However, if we replace the members of the series with their absolute values, we have this series. Yeah. And it's well known that, even though the numbers themselves are decreasing, they're decreasing slowly enough that this series just keeps increasing without bound. It doesn't converge, as the following argument shows, right? And there is then this example that this alternating harmonic series is conditionally convergent, but it's not absolutely convergent, right? And there's a famous theorem by Riemann called Riemann's rearrangement theorem, which shows that if you have these series which are conditionally convergent but they aren't absolutely convergent, then if I rearrange terms in the original series, like for instance, if I switch these two terms, etc. These are called rearrangements. I'm just permuting the terms. Then I can get them to converge conditionally to many things, in fact, to any real number. Okay. If you do real analysis, you can look up Riemann's rearrangement theorem and its proof, but this is completely outside the ambit of the TET course, right? We want to flag just one result here, which is that if I have a series that I know is absolutely convergent, then it's also convergent. It's conditionally convergent, right? So we showed that in the previous example that the converse is not true. There are series that are conditionally convergent, like the alternating harmonic series, that are not absolutely convergent, right? But if I know that the series is absolutely convergent, which here again to remind you means that the sequence of partial sums S tilde t defined as the additions of the absolute terms, right? So that's the sequence of these partial sums converges to a real number. Okay, if that is true, then the mother sequence, which is this, itself converges. Okay, so here's the proof. Suppose this sequence is absolutely convergent. That is that, the sequence of partial sums converges to a real number. Right? Then we know that the sequence of partial sums is a Cauchy sequence. Right? So because it's a Cauchy sequence, we can do the following. If we take any arbitrary epsilon greater than 0, no matter how small, there exists eventually a capital N such that with two indices, any t greater than or equal to capital N, we'll have that the distance or the difference between S tilde t and S tilde n, assessed in absolute value, is less than epsilon, right? So that's Cauchy convergence. But what is S tilde t? S tilde t is exactly this. What is S tilde capital N? It is exactly that. So the difference between these is exactly this sum. Okay, so what is being said is that the absolute value of this sum is less than epsilon. For a Cauchy sequence, I can find for the sequence of partial terms a capital N high enough that for every pair capital N and t beyond capital N, the difference in the partial sums is negligible, is less than epsilon, right? So that difference, because these are partial sums, is exactly the absolute of this sum. Okay. Notice that all of these are non-negative because they're absolute values. So in fact, I can remove the absolute sign. It's just that, these are less than epsilon, right? And you can see that this makes sense because if the series is absolutely convergent, then beyond a certain capital N, everything must become very, very, very small, practically zero, for there to be a limit, right? So now notice that I can apply a triangle inequality. I can say, look, I'll remove these absolute value signs and I'll add these terms from an plus 1 to at. Okay. And I'll ask, what is the absolute value of this, right? So by the triangle inequality applied several times, that's just less than or equal to, and you know that this is true, right? For absolute values. Yeah. I don't even need this outside absolute value here. You know that this is true. But we know that because the sequence of partial sums of the absolute value series is Cauchy convergent, that this is less than epsilon. But that means that the absolute value of the sums from the original sequence, an plus 1 to at, is also less than epsilon. But now notice that this is nothing but it's nothing but a1 plus a2 plus to at, okay, this partial sum st minus a1 plus a2 to an. Okay, so what is being said is that this sequence itself is Cauchy. Yeah, the partial sums without the absolute values, that's Cauchy, right? So this is a Cauchy sequence in R, which is a complete metric space, and so it converges, right? But that means that the mother series converges. Okay.